Okay, good morning, everyone. Today we're going to have the third lecture in this mini course on resurgence by Professor David Sauzin. Over to you, David.
Thank you, Pranav, and thank you again for this opportunity. So, yes, conclusion of this mini course where we have, so far, we have defined at the beginning endlessly continuable germs, and that would be via Borel transform, the definition of resurgence series. And then we have spent quite a lot of time with Borel transform, Laplace transform. So before returning to resurgence series, more on the Laplace transform. Suppose we have phi hat, a regular germ at the origin, with analytic continuation in a direction, let's say around the direction theta, with at most exponential growth at infinity. So there is some exponential bound at infinity, so that I can define the Laplace transform. So this is the picture. I have this direction and maybe this direction. And so maybe I have this tubular neighborhood, or maybe I have a sector, whatever. But at least around direction theta, with at most exponential bound, I can define L theta phi hat. This is a function of z, the Laplace integral. And this is holomorphic for real part of z exponential I theta large enough, depending on the exponential growth, the rate. And that is a half plane. And if you can vary the direction, you have more than a half plane. And uniformly in that half plane, you have asymptotic expansion given by the Borel transform, inverse Borel transform of the Taylor expansion at the origin. That was the story. Now, let us introduce a singular germ phi check. So phi check, not phi hat, sorry, phi check instead of hat. This will be singular, well, simply a logarithmic singularity. So this is a singular germ, well, singular at the origin. But apart from the singularity that we have created at the origin, we can follow the analytic continuation like before. And why do I do that? Of course, you have phi hat is nothing but the variation, the monodromy of phi check, which means that if I consider a Hankel contour in direction theta, so I'm coming from direction theta minus 2 pi from infinity, turning around the origin and going back to infinity, but in direction theta, then we have that the usual Laplace transform is nothing but the integral along this Hankel contour. Well, let me use this notation of the singular germ. So it's let me introduce a notation for that. So when you see this integral, direction theta, Hankel contour, so this is the Hankel Laplace integral. Let me denote it by Laplace triangle theta for phi check. Phi check. So this is a notation. So which we can apply in this case. But we can apply it in other situations. So why is this identity true? Well, you can see that this integral here, you have twice the same half-ray. Well, you stop a little bit before the origin and then you have a circle. So the point is that, let me stop at epsilon in direction I theta. So I'm coming from epsilon exponential I theta minus 2 pi. So this is this part. And then I have the little circle. So I have a sum of two terms. Clearly the first term, well, you just collect the variation along one half-ray starting from epsilon. So it's the Laplace integral starting from epsilon. Let's send epsilon. Let me send epsilon to 0. And then I will recover exactly the Laplace transform. While the other term, when epsilon tends to 0, it's a small circle of, it will tend, the contribution tends to 0 because it's singular, but it's a mild singularity. You see, it's, well, the integral of that on a circle of radius epsilon tends to 0 as epsilon tends to 0. So this is how we prove that formula. So this is the Hankel Laplace transform of a singular germ. Good. We can do that not only for logarithmic singularity. Let me do it now for another situation. Suppose we have beta, a complex number, not integer, and with positive real part. And then you remember, maybe it's, you can also consider phi hat, little phi hat, zeta to the beta minus 1 phi hat. So this is not exactly a regular germ. It has a singularity, but it's an integrable singularity. You see, this is why I put this condition. It's integrable at the origin. So the Laplace transform of phi hat at the origin, no problem. So the Laplace transform of this phi hat is well defined. This is a function of z like before. And similarly, I didn't give any detail, of course, but similarly, there will be an asymptotic expansion at infinity, which is given by inverse Borel transform of the expansion at the origin. But in the expansion at the origin, now we have non-integer powers. So in the expansion at infinity, you have non-integer powers of z, but no problem. And formally, this is small at infinity. It tends to 0 at infinity. Good. So now, can we adapt our philosophy to that situation? Yes, we just need to preserve that relation. So what is phi check in that case? So I want to write this little phi hat as monodromy of phi check. So I just use For instance, I'm not saying there is only one possibility. Clearly, once you have found one phi check, you can add anything regular at the origin, and you will not spoil the formula. In that case, let's say we divide by this. So we take the same formula, but we divide by 1 minus exponential minus 2 pi I beta. And that will do. And again, for this phi check, I can use this formula, play the same game, and I find the same result. The Hankel Laplace transform gives me what I want. Okay. So these two functions of z are equal. And now what is the gain? What is the advantage? The advantage is that this Hankel Laplace transform can be applied to a wider class of singular germs. So L triangle can be applied to a wider class of singular germs. So let me give an example. So not just these ones. So for the moment, we have seen logarithmic singularities. We have seen that kind of integrable singularity. We could do a simple pole. So e.g., what is the Hankel Laplace transform of this simple pole? So this is not regular at the origin, not integrable. And you see the monodromy here is 0. So the contribution of this is 0. But the contribution of the circle is given by residue formula, it's 1. So this function of z is the constant function 1. So you see, you can introduce the function delta check to be 1 over 2 pi I zeta. And similarly, you can also consider its derivative. So this one is mapped to 1. Its derivative, so it has a double pole. You can apply the residue formula, or maybe you know that Laplace of the derivative, this is z times Laplace. So you get z, etc. So z power k, or 1, can be realized now as a true Hankel Laplace integral, not just a symbol. Because you remember we had this delta, which was a symbol of which the Laplace transform was 1, and it was defined as the formal Borel image of 1. But now it has a meaning as not as a distribution, as a singular germ at the origin. That's the point. And also this formula here. I said real part of beta positive is needed to write it like this. But if real part of beta is not negative, this is still well defined. So you see, we have access to a wider class of singularity. And we could give many more examples, but so the point is that this one also is well defined for any beta non-integer, of course, because we divide by it. So we can enlarge the framework of Borel-Laplace this way. And well, keep in mind this idea of Hankel contour, because it's very important for what follows. Let me see an example now. Let me show you an example. I like examples And this one, so we had seen already noble examples, the Euler series, the Stirling series. Here is the Hurwitz zeta function. Hurwitz zeta function. It is defined, well, let me use phi s of z. The traditional notation would be zeta of s and z. So this is defined to be this series, z plus k power s for all non-negative integers. And so clearly we need something to ensure convergence. We need, so s can be complex, but real part of s is larger than 1. And well, you see this z, well, I can say it's in the cut plane. You see, because here, imagine s is integer. Imagine s is 2, 3, 4. We have poles of order s at 0, minus 1, minus 2. But if s is non-integer, then we have branching points. So, well, we do a cut. And then if s is non-integer, I need to specify which branch I am using here. So let me say it's the principal branch considering that argument of z is between minus pi and pi. So I view this cut plane as a subset of the Riemann surface of the logarithm. And we are in this situation. And of course, z plus k with k integer has argument between minus pi and pi. And so this is well defined. So this is a holomorphic function of two variables, s and z. And it's an exercise to show using the functional equation. So exercise, use the functional equation phi s of z minus phi s of z plus 1 is equal to just the k equals 0, z to the minus s, to obtain the following formula. Phi s of z is the Laplace transform of phi hat s. Well, in a certain interval, so it's not just one direction, you can vary in a sector with, so phi hat s of zeta. What is it? Well, you can see it here. I mean, it's the Borel transform of this, zeta power s minus 1 divided by gamma of s. And here you have 1 minus exponential minus zeta coming from here. Well, I'm going a bit fast, but it's very similar to what we did with the Stirling series and the functional equation for mu. It's exactly the same. So so now, what is the picture in the zeta plane? You see that we are dividing by something which vanishes at all integer multiples of 2 pi I. So let me factor out zeta so that, well, zeta minus 1, so that what is left has no more singularity at the origin. So you see that because zeta over 1 minus exponential minus zeta is meromorphic with no pole at the origin, but the poles are simple poles at in non-zero integer multiples of 2 pi I. And now, what is J? It's this And j is minus pi over 2 plus pi over 2. Okay, you can prove that. Good. That's already an information. It gives you the asymptotic expansion as z tends to infinity in that domain, real part of s larger than 1. And then, of course, if you want uniform asymptotic expansion property, you need to specify a subsector, and then you have not exactly the full cut plane, but you have a large sector, a large sectorial neighborhood of infinity within the cut plane. That's already good. So Laplace transform is good to give you asymptotic information, but it's also good to give you the domain of analyticity, because look at this. Is it really necessary to suppose real part of S larger than 1? It was necessary to ensure convergence here. It is necessary here to ensure integrability. I mean, Laplace is not defined. This Laplace is not defined if I'm not ensuring integrability. But now I can use Laplace triangle in the same directions. I can do that introducing, so I need to introduce something with the appropriate monodromy. Well, I just, well, now I will I will assume S is not integer. And this way, it's clear what I should do. I should divide. So I have 1 over gamma of S, 1 over 1 minus exponential minus 2 pi is, and the rest as before. Okay. So now I'm saying if real part of S is larger than 1 and S is non-integer, then I can rewrite my integral like this. But now I see, well, the analytic continuation when real part of S is no longer larger than 1 is possible because this integral does not require integrability at the origin, because I'm avoiding the origin, I'm circling around. So this gives me an analytic continuation. In fact, so it gives me an analytic continuation where? So I started in real part of S larger than 1 times this sector, this subset of the Riemann surface of the logarithm. So that was what I started with. And now I get, where do I get it? This factor, I said as non-integer because I was dividing, but gamma has poles at negative integers and at the origin. So these poles will cancel the vanishing. So in fact, well, you can use the reflection formula. This is the same as exponential I pi s over 2 pi I gamma of 1 minus s. So really what you should avoid is positive integers. 0 and negative integers are not poles of that factor. So we get the analytic continuation for all real part of S less than 1. So in the end, we have, except S equal 1. S equal 1, we can never have it. I mean, at 0, minus 1, etc., the pole is removed. But at S equal 1, you cannot remove it. Well, that's a fact. By the way, when Z is 1, you recover Riemann zeta function. And you know that Riemann zeta function has analytic continuation with a pole at S equal 1. And we have proved the same fact. I mean, this is a proof of the analytic, of the meromorphic continuation of the Riemann zeta function as a particular case. So the final result is C minus 1 times the same as before for Z. Yes. Yes, phi, the Riemann the Hurwitz zeta function is the Laplace transform of an endlessly continuable germ. I mean, it's meromorphic. In particular, it is resurgent. I mean, the series, the asymptotic series is a resurgent series. Hence, the function can be declared to be itself a resurgent function. Yes. But you see that the representation of a function as Laplace of something gives you good asymptotic properties at infinity, gives you information on the non-trivial information on the domain of analyticity. And usually what you want to do, and this is the next part of the talk, you want to compare, I mean, why are we using always J? These directions. Why do not we use these other directions, and why don't we compare the two? So this is the Stokes phenomenon. So then this is another step which provides, again, valuable information. So let me close this example here and go to a definition now. Now I want to go toward resurgent series and simple resurgent series. So let me define, first of all, simple singularities. So definition, we say that a singular germ like phi check, singular germ at the origin, we say that it has a simple singularity at the origin if it can be written as a pole of order 1 plus a logarithmic singularity, phi check, plus something regular. So here, anything in the space of regular germs. C is any constant, and phi hat, sorry, is any regular germ. So this is a mixture of two examples that we have seen before. So this is a singular germ at the origin. It is a singularity, but it is a simple singularity because it's simple pole plus logarithmic with regular monodromy, regular variation. Phi hat is nothing but the variation of phi check. But phi check is not as mild as before because potentially it has this simple pole part. Okay, in that situation, we use the notation sing at 0 of that guy, phi check. We use the notation C Dirac plus phi hat. So for the sake of simplicity, we will focus on simple singularities, but we could envision much wilder singularities. I mean, let's start with something easy. I mean, we could also consider, so it's a remark, one could consider singularity of, so if you have, well, like delta check differentiated k times. So that's something like this. So if your singular germ has a pole of order k plus 1, the natural definition is Sing 0 is not Dirac, but Dirac differentiated k times, because Hankel Laplace transform will map it to z power k. If you see something like well, of course, 1 over 1 minus exponential 2 pi I nu zeta nu minus 1 over gamma nu. Okay, again, it would be, well, let me use this notation, delta to the minus nu. And this is for any nu non-integer. So if nu has positive real part, it's integrable, so the Hankel Laplace transform will boil down to a usual Laplace transform. If not, we are doing something different. We are enlarging the framework. And another one is, well, now imagine we encounter this with beta non-integer. Well, if real part of beta is positive, you will say, and if beta is non-integer, well, this has a singularity at the origin. How do I encode it? So the notation, the meaningful notation is you compute the variation because it's integrable, so it will capture the singularity. You will not lose any information. And then the meaningful notation is to say, well, you see, well, I need not Borel. I mean, in my notation, here I put zeta power beta minus 1 phi hat itself. I put the germ whose usual Laplace transform will give me what the Hankel Laplace transform would have given. This is the trick. Okay. So that's about singularities. Just a few examples, but you can, in resurgent theory, I mean, you can cover much wider singularities. It's just a question of time and clarity. We focus on those examples, but virtually you can cover any kind of isolated singularity. For instance, so this gives us z power minus nu, and nu is any. But for instance, can you imagine what will give you z minus nu times logarithm of z? So where does it come from, by Laplace or Hankel Laplace? Or if you have a power here, how do you obtain it? Well, it's an exercise. Differentiate with respect to nu here. If you differentiate in nu, you get these guys. So this is the idea, differentiate this formula in nu and you get a certain kind of singularities, mixing powers and logarithms of zeta. But here you have the proper encoding, the encoding which is compatible with Hankel Laplace and Laplace. This is what we want. Good. Now we said, that was the first course, I think, the first talk. The first lecture said that resurgent series, let me put a tilde always on formal objects. So resurgent series were defined as Borel inverse of, well, constant multiples of Dirac, accounting for multiples of 1, plus endlessly continuable germs at the origin, regular germs in. So that was the definition. A formal series is resurgent if it's Borel transform. Well, you discard the Dirac and you are left with a germ. It should be convergent and it should have that property of analytic continuation. Let me show you interesting subspaces. Interesting subspaces. They will be denoted R tilde omega. So this is, it is defined for, well, the definition is Borel inverse of C Dirac plus R hat omega. So I need to define R hat omega for omega, a subset of C, non-empty, closed, and discrete. So this means I will fix in advance the possible singular locus. So it's simpler in a sense. So let me write it here. R hat omega is defined to be the space of omega continuable germs. What does it mean? You fix in advance omega, a set, maybe infinite, maybe a lattice, maybe finite subset, anything closed, discrete, non-empty. And you have your germ, phi hat. And the meaning is that any path which starts in the disk of convergence, imagine this is the origin, this is the disk of convergence. Any path which starts in that disk and which avoids omega is a path of analytic continuation. Analytic continuation is always possible provided you avoid omega. So this is a particular case of endless continuability, but it's simpler because you have fixed in advance the possible obstacles to analytic continuation. And I said interesting subspaces. So for each omega, you have such a subspace. And you have also R tilde simp and R tilde omega simp. So many definitions. What is this? Those resurgent series such that the Borel transform, so C Dirac plus phi hat, is such that all the singularities of the analytic continuation of phi hat. So it is resurgent. So we know in advance that phi hat is convergent and has an analytic continuation to a very large Riemann surface, endless. But there are obstacles. These obstacles are the singularities. All of them are simple singularities in that sense. In that sense. Of course, we have to shift the definition. That was simple singularity at zero. Now I'm saying for these guys, when I follow the analytic continuation and I approach a possible singular point here. So I'm following my path gamma. So I'm following a path gamma. I'm following the analytic continuation. And maybe there is a singularity at omega here. So when I arrive close to omega, so I have followed the analytic continuation, and I am close to omega. So let me call psi the distance which is left here. Well, I would like this germ, possibly singular at omega, to be of that form. Is, well, has a simple singularity at psi equals 0. And that is the meaning of the analytic continuation of phi hat has a simple singularity at omega. So quite natural. So all the singular are simple. And similarly, well, this is just the intersection. Simple singularities, and they are located on omega. Okay, let us have a look at.
Can I just ask one question? Yeah, I just wanted to know, do you have to specify the singularities on all Riemann surfaces, on all the plane Riemann sheets?
Yes, really all of them, absolutely. We are envisioning here the analytic continuation of a hat along all paths. And some of the paths are not path of analytic continuation because they are obstacles, but we have said these obstacles may be isolated. And here I'm assuming, well, moreover, the obstacle corresponds to a simple singularity.
Okay.
Okay.
So that could be infinite number of these, if you count all the Riemann sheets.
An infinite number of
obstacles.
I didn't hear the word.
Yeah. Could there be infinite number of obstacles? I mean, is this a finite number or?
All obstacles can be infinite, yes. In fact, it's very convenient when you have omega fixed, closed, discrete, okay. But sometimes you cannot. I mean, not all resurgent series belong to one of that spaces. Sometimes you find in nature series which are here, and you cannot define a closed discrete subspace because, yes, the singularities are isolated, but when you take all of them in projection onto C, they are dense. So it's possible that there are very, very numerous singularities. So you cannot, yeah.
Thank you.
The possible singular locus may be huge in practice.
So sorry, I didn't understand. Are you saying that in general, you might even assume that omega is not closed?
Yes, that would be the idea.
You could
yes.
take omega to be something.
In some sense, yes.
Okay.
Yeah. It's just that this definition doesn't make too much sense. The definition I gave, if omega is not closed. So this is why, I mean, when we do not fix omega, when we say endless continuable, you remember it was, you fix in advance the maximal length. So for each capital L, there exists a finite set such that the length the path of length less than L, which avoid that set. But then you let the length increase, so the singular locus is countable, but it may be dense, it may be anything. Okay. Now, oh yes, examples, because we have a few examples so far. So I think it's good to have a look. You remember, well, if the Borel transform happens to be meromorphic, then analytic continuation is easy, clear, and you will have simple singularities if and only if the poles are just simple poles. So that was the case of you remember the Euler series, let me call it phi hat E, so that the Borel transform of the Euler series was just 1/1 plus zeta. So clearly, here we are in the case of something simple, and here we have just one pole, okay? We have seen an example of something algebraic. It was you remember, we had this Z, maybe the second example. So Z tilde was its asymptotic expansion. It was, well, a power series in 1/Z. But if you multiply by little z power -3/2, then you get a germ which is singular at the origin with a square root, because, well, you have multiplied by, so the constant term multiplied by z to the -3/2. The Borel transform is zeta 1/2 divided by gamma of 3/2, which is 1/2 square root of pi. So I was about to write this, and we remember it was algebraic. So clearly it had endless analytic continuation. So we can be more specific. Here it's something like this. And so here there is a singularity at 0 and at -1/16. And because it's algebraic, you have under control the whole analytic continuation. So this is very simple example. Another simple example, but with another kind of multivaluedness. Take, let me denote it by, I don't know, chi hat. Let me take the logarithm, and I put this -1/zeta in front. So you see we have an honest Taylor series at the origin. So we have something certainly very regular. And clearly there is an endless analytic continuation, not meromorphic, but endless, yes. And what kind of singularities will we meet? Well, at zeta = 1, there is a singularity, which is a logarithm multiply, well, we shift at 1. So we have a meromorphic thing, but locally near zeta = 1, it's regular times logarithm. So it's a simple singularity. So we could write something like this. It's simple, and the singularity is at 1, but there is also a singularity at the origin, because the principal branch has no singularity, but once you have turned around 1, and when you come back, you see a pole, a simple pole at the origin that you could not see on the principal branch. And if you turn, you change the residuum of the pole. So simple example. And by the way, it's also a noble example if you take its primitive is nothing but the dilogarithm function. The primitive of this is the so-called Euler dilogarithm. So yes, it is resurgent. Well, in the Borel plane, we say endlessly continuable. The possible singularities are located at 0 and 1. And when you integrate a logarithm, a simple singularity, it stays simple, because the simple pole gives rise to a logarithm. When I say logarithm, here I must say I'm using the principal branch to say which series I'm manipulating exactly. But in the definition, remember, simple singularity, it's something plus possibly something regular. So if you change the branch of the logarithm, you are just adding something regular, so it doesn't matter. Okay, we have seen the Hurwitz example. How was it? This phi s hat. Well, there was this zeta power s minus 2 in front, and now it was meromorphic again. So 2 pi I z star in that case. So meromorphic, well, meromorphic, but on the Riemann surface of the logarithm in the zeta plane, unless S is integer, of course. Oh, yes. And now the Stirling series, I want to show you at least something non-meromorphic, something really more complicated and still explicit. So this is the trouble with resurgence. Many examples are a bit too simple. Well, it's meromorphic, algebraic. And so Stirling was very simple. You remember mu hat was a very concrete, I don't repeat, well, yes, the formula was this. Let me repeat the formula. So a very concrete meromorphic function. So yes, it was endlessly continuable, singularities, well, meromorphic, simple poles, very simple. Now, let me consider another one, related one. And it's much more complicated. Do you know the Lumbar W function? So it's obtained by solving W exponential W equal to X. So you look for W function of X satisfying this. If you stick to the reals, you can look at the graph and you understand the branches, etc. And then you go to the complex. Well, and there are many branches. So, but among all the branches, you have two real branches. That's a well-known fact. So let us denote by W0 of X larger than W of -1 of X. So these are standard notations in the literature. So these are the two real branches of Lumbar W function. So it's something in the literature you can find, and they will show you that the Lumbar W function, well, it's an example of endlessly continuable functions. And all the possible singularities, well, for instance, the real branches, this is for X between minus exponential -1 and 0. And 0 is a singularity for W -1. And minus exponential -1 is a singularity. It's square root branching for both of them. And these are all the possible singular points for all the branches. Okay, now let me consider 1 over square root of 2 pi, W0 minus W -1, evaluated on minus exponential 1 minus 1 minus exponential -1 minus zeta. So I take the difference. In fact, I told you near that point, it's a square root branching, two branches of the same. Well, it's because, well, we are inverting a function which has a critical value. So, I mean, this exponential -1 is the critical value. So this is why this difference is non-zero, and it has a Puiseux expansion with half integer powers. Okay, so I consider this difference and evaluate it here. And I get something which is, well, you can compute it. Zeta 1/2 over gamma of 3/2 plus etc. I mean, only half integer powers. You can compute the Puiseux expansion. And now, where will it be singular? I told you where all the possible singularities of the branches of the Lumbar W function. So you will never hit 0, but you will hit this whenever zeta is integer multiple of 2 pi I. So this guy is resurgent 2 pi I, well, and endlessly continuable, it's 2 pi I z continuable, but there is the zeta 1/2 in front. Okay, So why did I consider this? It's because this, let me call it lambda hat 3/2. In fact, I consider it because Laplace of lambda hat 3/2 is nothing but z to the minus 3/2 lambda, where lambda is exponential mu, which is, and mu, you remember, mu is Laplace of mu hat. I mean, this is the normalized gamma function. So what is it, z to the minus 1/2, something like this. So this is the funny thing. The logarithm of gamma normalized had a very elementary Borel transform. But gamma normalized itself, it has an asymptotic expansion at infinity, which is just the exponential of the previous one. But what is its Borel transform? What is the Borel transform of the exponential of something nice? It's usually not very nice. But here, miracle, there is a formula, not exactly for lambda, but for lambda multiplied by z to the minus 3/2. It's here. And well, you see, it's strongly multivalued. I mean, this is the point of this example. Here we had multivaluedness due to the logarithm, but it was very elementary. But here it's multivaluedness due to solving an implicit function problem with critical points, and moreover, we have inserted the exponential. So it's a beautiful example, which was motivated by the formula Maxim Kontsevich showed to me a few years ago. Now we are ready to define alien operators. So we have said a little more on resurgent series. We have the big space, subspaces may be more tractable, like this one is more tractable because the singularities are simple and we know in advance where they are located. Now let us discuss these alien operators. So we will define two families of operators, the delta omega plus and the delta omega. And the delta omega were announced in the first lecture as being the alien derivations. So for the sake of simplicity, most of the time we stick to our simp. So let's take phi tilde. We compute its Borel transform. We throw away the Dirac part. We are left with a germ, phi hat, which is endlessly continuable. Good. And we have assumed that wherever they are, the singularities are simple. So let me pick now omega, a complex number. And I will do something with phi hat and omega, knowing that all the branches of phi hat near omega, what I mean is I imagine any path coming close enough to omega, close enough so that I can say Maybe there is a singularity at omega, maybe not, but locally there is nothing else. I'm close enough so that omega is the only singularity I see here. Now, close to omega, all the branches are of the form so when I say branches, so I mean continuation along a certain path gamma, and I'm arriving close to omega. So let me say zeta is close enough to omega. And I have a constant divided by 2 pi I zeta minus omega, because it's a simple singularity plus logarithmic singularity. So there is a psi hat of zeta minus omega logarithm zeta minus omega plus something regular at omega. And everything here depends on omega and on gamma. Depends on the branch. All of them are like that. So in particular, for gamma, I could try to look at the straight segment. I'm starting from the origin, and I have my omega somewhere, and I would like to go in straight line. But possibly there are obstacles, intermediary obstacles. So obstacles, I put crosses. But I'm interested on these obstacles on the straight segment. And there is the idea that maybe for one of the branches, omega is a singular point, or maybe not, in which case, no problem. We will declare that the operator acts by 0. But the interesting case is when omega is one of the potentially singular points. So what could I do? I could choose particular path. I mean, a particular path is the path which starts from 0 and avoid all intermediary singular point to the right. And now I am close to omega. So this path, let me call it gamma plus. Plus means to the right, minus means to the left. So this is a path which goes always to the right. Well, of course, very small circle, because maybe there are other singularities and I don't want to interfere with them. Of course, I will not make a detour and capture another. I mean, no, I'm as close as possible to the straight line, circumventing to the right the intermediary singular points. And now I define delta plus omega of phi tilde to be well, C omega gamma plus psi hat B inverse of psi hat omega gamma plus. In other words, I define delta plus to be my encoding of the singularity at omega. So remember the notation sing 0. I have followed the analytic continuation along gamma plus of phi hat. I have shifted my variable. I'm close to omega. And now this is a singular germ at zeta equals 0. And I have my notation. I take the singularity. It's supposed to be simple, so it has a very clear meaning. And here, because phi tilde was a formal series, I take Borel inverse, and I get a formal series. Because I have assumed that all the singularities were simple. But I can say more on it. This formal series, when I will compute its Borel transform, I will find C Dirac plus psi hat. What can you say about psi hat? Psi hat is the monodromy of that singularity. Psi hat, you obtain it by computing the difference of these two branches here. So psi hat up to the shift of the variable is obtained as a difference of two branches. And all the branches have endless analytic continuation. So psi hat must have endless analytic continuation. So in fact, this is a resurgent series because its Borel transform is endlessly continuable just because it is the difference of two branches and we have shifted. Well, where are the singularities for this guy? Imagine a particular case, maybe phi hat was in one of these omega. Particular case of what I said. Imagine, well, that was known in advance, it was omega. Then, in that case, where would be the singularities? Well, minus omega plus omega, because of the shift here. So my operator, I'm defining an operator delta omega plus. So let's say omega is fixed. Of course, if I assume this, then I'd better take omega in omega. So in general, I take any omega, non-zero, and I do this. And I start with a resurgent simple singularity. I get a resurgent simple singularity because, yes, it is simple because, again, how do I know it is simple? I will look at the singularities of the analytic continuation of psi hat, which is just the difference of two particular branches of phi hat. So we have defined delta omega plus from R tilde sim to itself. And in general, it maps R simp omega to R simp minus omega plus omega. And now, slightly more complicated, let's have a look at delta omega. Delta omega. Now, I will not restrict my attention to this path, which turns always to the right. I will also consider a path which turns left, or left and then right. So there are many of them. In fact, this path, I can encode them by a symbol epsilon, epsilon underline, a sequence of pluses or minuses. So let me say, I number my intermediary singularities, omega 1, omega 2, etc. Omega is the one I want to reach. Omega is omega r. So there are r minus 1 intermediary singularities. For each of them, I must decide whether I circumvent them to the left or to the right. So I choose a plus, a sign, plus or minus. So I have 2 to the r minus 1 choices for epsilon. And I consider these, all these 2 to the r minus 1 path. And I use the same formula. So delta now is defined to be, so I take a sum over all possible epsilons Borel inverse of the singularity of, but I must take some average, some balanced average of these singularities. So continuation along gamma epsilon of phi hat at omega plus zeta. Omega is omega r. And I take the singularity. And there is a coefficient. Sorry, I had put the sum in front. But the coefficient is, well, so, I mean, I don't know why I put, I mean, everything commutes here. So Borel inverse singularity at 0 of. So P is the number of pluses. Q is the number of minuses. And P plus Q is just R minus 1. So it's a funny combinatorial coefficient. It is designed to ensure that this is really a well-balanced average. For instance, it's a remark. If phi hat is single-valued, meromorphic, if in reality there is no multivaluedness, singularities but no multivaluedness, then the sum of the coefficients is 1, and in fact, delta and delta plus coincide. This is just to reassure you that this choice of coefficients is really a good idea. What else can I say at this level? Oh, we will see it now. Yes, yes. Very good question. Sorry? Yeah, but we will, that's the next theorem. Well, maybe, okay, that's the theorem now. That's the theorem now, exactly. Theorem. So again, same story. Delta omega maps resurgence simple series to themselves, and the same kind of action on the location of singularities. We are just measuring singularities after shifting the variable, just that. But here we have this strange combinatorial recipe. Theorem. R tilde and R tilde simp are subalgebras of the algebra of power series. So meaning stable on the product, essentially. And these operators satisfy the Leibniz rule. The last ones, and the delta. The delta omegas satisfy the Leibniz rule. Not the delta plus. The delta plus are easier, but the Leibniz rule is for delta, which is more complicated. So this is why the delta are called alien derivations. There are derivations. Delta omega. By definition, this is the alien derivation at omega. That's its name. Another property is that there is a natural derivation, d over dz. It almost commutes with delta omega. So you can compute this. I mean, this is an exercise. I think it's not difficult if you remember that Borel transform of d over dz is multiplication by minus zeta of the Borel transform, multiplication of minus zeta. Well, this is easy to track through analytic continuation. So in this formula, you have multiplication by minus zeta becomes by minus omega minus zeta. So there is a twist here, minus omega. This is why you end up with this formula. So apart from that, there is no relation with the natural derivations. This is why they were called alien, because they are really, I mean, this would be the natural one. Okay, and sure. Yes, this is what we do now. Indeed, to motivate this, I mean, at that point, it looks a bit mysterious, but there is, I think, something quite convincing using Laplace and Hankel Laplace, which will somehow justify all this business. I'm sorry, I must speed up a little bit, but okay. Where do I put that? 675. Yes. It's here. Suppose we have this situation, direction theta prime larger, and in between, for the sake of simplicity again, you have no singularity except on that ray. And on that ray, you have singularities, omega 1, omega 2. So I'm speaking of a particular germ, phi hat. And when I follow this analytic continuation in this sector, I see singularities here, but nowhere else. So in that situation, what do I want to do? I want to compare the two Laplace transforms, that one and that one. So let me compute L theta minus L theta prime. So this is an integral like that of the Laplace. Well, if phi hat is meromorphic, you know how to do that. You will push the contour using Cauchy theorem, and so you push it like this. And when you arrive here, you say, well, but this is the same as doing this, and then a circle, and then this. If it's meromorphic, well, I close the circle. This is one contribution, and I go on pushing that one. And in the end, I am left with the sum of the contribution of each singularities. This is quite standard trick in complex analysis. Now, here we are considering a phi hat, which would be the Borel transform of a simple resurgent series. So maybe they are not just simple poles. Maybe together with the simple poles, they are logarithmic singularities. So how is it modified, this process? Well, here is the modification. You want to go from infinity in that direction toward infinity in that direction. So you go from infinity direction theta prime, and you circle around theta omega 1, and you go back to infinity, and now you come back and you circle around omega 2, etc. And you find sum over all m's of such integrals based at omega m and direction theta prime, etc., of the same thing. So now you can shift your integration variable zeta, and you see that you have, this is not a very good color, I'm afraid. So you have, when you shift the variable, you have exponential minus omega mz coming out. And now we have our Hankel contour now is back at the origin. So we have the Hankel Laplace direction theta prime of a singular germ. What is this singular germ? It is a singularity at 0 after shifting. So, but look at this. So it is the singularity at omega m of something which comes from the right always. So in fact, this is delta plus. And here I'm forgetting Borel. Yes, it's Laplace of Borel. It's Hankel Laplace of Borel of delta plus. So this formula says that, I mean, I'm very quick, I'm sorry, but L theta appears to be the same. So L theta of, so phi hat was Borel of phi tilde. So L theta Borel is the same thing as L theta prime Borel of composed with identity plus this graded series, this series over m exponential minus omega mz, and it's delta plus omega m. Now, take for granted that R tilde is a subalgebra. So take it for granted. Now, you remember the Borel transform will map a product on the convolution, and the Laplace transform will map the convolution on the product. So we are mapping here the product of series to the product of functions. So this is a homomorphism for the multiplication. And the same here. So this guy in between, this is an homomorphism composed with the inverse of another homomorphism. So it is an automorphism. It must be an automorphism. And what is the reason for these funny coefficients? It's exactly what you need in order to write this. The logarithm of that homomorphism, so logarithm in a graded sense. I mean, if you consider that these exponentials here, they correspond to some grading, and it makes sense to speak of infinite series and to take the logarithm of identity plus something. And that's a super general logarithm of an automorphism must be a derivation. And so now the delta omega m are the homogeneous components of a derivation. So this is the directional alien derivation associated with the direction from theta to theta prime. I mean, it's essentially associated with that particular direction, theta star, and you imagine theta and theta prime are infinitely close. So there is this directional alien derivation in the direction of theta star. It must be a derivation because it's the logarithm of an automorphism. And that automorphism is very important for us because in practice, we are comparing to Laplace transform. So we are computing a Stokes phenomenon. I mean, it's interesting for us. Now, the homogeneous components of derivation are derivations. So this is why the delta omegas are derivations. Of course, it's a bit difficult to make a proof with that. It's possible, but you see, there are many technical assumptions. Here we need at most exponential growth at infinity to guarantee that the Laplace transform are defined. We need to ensure the convergence of these series, convergence in M, etc. But well, it works in all cases. You don't need these assumptions. It's a combinatorial fact that you can prove by hand by looking at the definitions. Okay. I must conclude in a few minutes. So before concluding, let me show you one non-trivial example of computation. Well, not non-trivial, but very elementary, though. So we had the Stirling series mu. Well, sorry, mu was the function, logarithm of the normalized gamma function. Mu tilde was its asymptotic expansion, and we know that it is resurgent simple series because its Borel transform is meromorphic. So it's easy to compute delta omega when omega is, in that case, it's 2 pi im. And you just have to compute the residue and to use the proper encoding of singularities. You remember there is the 1 over 2 pi I, etc. So when you do that, you find exactly 1 over m. Now, what about lambda tilde? Lambda tilde exponential mu tilde is the asymptotic expansion of the normalized gamma function itself. So what about itself, this guy? So it is a resurgent simple singularity, simple resurgent function, a series. I will try to explain why the singularities are 2 pi iz, including the origin. I mean, this one was meromorphic, but this one has a Borel transform which is multi-valued, and the origin is not a singularity on the principal branch, but it is for the other branches. And you can compute the alien derivative of lambda tilde by alien chain rule. I mean, you can do alien calculus now. Look at this. What is the derivative of an exponential? Well, if really it's a derivation, it cannot be anything else but this. And this can be justified, and you find 1 over m lambda tilde. Alien derivative of lambda tilde is proportional to itself. Well, and this, just a tiny digression, we could have guessed that. I mean, maybe it was not so easy to guess this 1 over m without doing the computation. But why do I say we could guess it? I mean, I want to illustrate the power of ÉCALLE's philosophy. Lambda tilde is the gamma function normalized. So it satisfies a linear difference equation. You can compute an A of Z such that this is true. A of Z is something explicit, convergent at infinity, coming from the functional equation of gamma. So we are speaking of a particular solution to that equation. Now, delta omega commutes with the shift operator. Let me call this TZ, the shift. Why does it commute? I said it does not commute with d over dz, not exactly. But the shift is exponential d over dz. And omega is 2 pi im. And exponential 2 pi I m So when you exponentiate, you find 1. So it's very simple, but delta omega does commute with the shift if omega is multiple of 2 pi I. So I can apply delta omega to the equation itself. What is delta omega of the left-hand side? Delta omega of the shift of lambda tilde is the shift of delta omega of lambda tilde. What is delta omega of the right-hand side? It's delta omega of a product, Leibniz rule, but A is convergent. What is delta omega of a convergent series? The Borel transform is entire. There is no singularity to be measured. You find 0. So there is only one term left in the Leibniz formula. So we have proved that lambda tilde and its alien derivative satisfy the same linear equation. So when you consider the ratio delta omega lambda tilde over lambda tilde, you knew in advance it had to be constant because this ratio formally should be periodic and within the space of formal series, being a shift invariant means being constant. So that's very powerful, this philosophy, because it works in nonlinear situations as well. Maybe it's about time to conclude. So let me show you, oh yes, I must show you a picture. How can one prove that R tilde and R tilde simp are subalgebras? The point is that what happens when you multiply formal series in the Borel plane, you take convolution. So let me recall the formula for convolution. So let me take two functions. So this is the convolution. And this is well defined for zeta close enough to the origin. And now I'm assuming that both F and G have analytic continuation. Imagine, for the sake of simplicity, this one has analytic continuation, and there is a set omega, let me call it A. And for G, there is a set, let me call it B. So all singularities, I assume, will be contained in these sets. And I wish to prove that the convolution product is still endlessly continuable, and in fact, it will be A plus B, or well, I should say A union B union A plus B. So of course, you keep the singularities of F, you keep the singularities of G, but you may create new singularities at the sums. Why is that so? So there is here something I would like to show. So now I will share my screen. So I don't know if it works for Zoom. It would be nice to have it.
We see it on Zoom, but let me just ask the AV team.
Yes, I see.
Could you please project the screen?
I see that it will come. And while it's coming, yes. In fact, the proof of that fact is adapted from an idea which can be read in a paper by Émile Borel. Émile Borel was interested in the Hadamard product. I'm speaking of 1895, something like, or 1900 maybe, well more than 100 years ago. I mean, it's a beautiful story. Hadamard had written his famous paper about the Hadamard, now it's called the Hadamard product, the composition of singularities. And Borel was fascinated by that, and he designed his own proof. And usually Hadamard product and the theorem about the singularities, it's more on the principal branch. But Borel was thinking a little bit about the other branches. But not, well, you have to read it. So now when you adapt what Borel says about Hadamard product to the convolution product, well, Hadamard product is a multiplicative convolution. This is additive convolution. Here is the idea. The expression of f star g stays valid, this expression, as an integral along a contour. Here you have a straight segment, but it need not be a straight segment. It stays valid if one deforms the integration contour without letting it cross any singular point of the integrand. So singular point of the integrand, zeta1 should not be in A, and zeta minus zeta1 should not be in B. So zeta1 should not be in zeta minus B. So these are the singularities of the integrand. And the contour having been fixed in an arbitrary manner, one obtains the analytic continuation of f star g by moving psi in the plane, provided the singular points, when you move, these singular points move. But as long as the singular points of the integrand do not cross the integration contour, it's okay, you are dealing with the analytic continuation. So let us conceive the contour, integration contour, as a flexible, extensible thread. The singular points of f of psi1, zeta1 as pins stuck into the plane. So you have pins. So we start like this. So we want to follow the analytic continuation along gamma. So this is, we have reached this point. So instead of zeta here, it's psi. So at that point, we can use the straight segment, no problem. But this is an extensible thread, and now we will move psi toward psi prime. So let us imagine that what is the matter? We have fixed nails, pins, stuck into the plane, which materialize the singularities of f. And the singularities of g of zeta minus zeta1, these are moving nails located at zeta minus b, so they move. Pins that travel as zeta move. It is necessary and sufficient that the thread always part the two systems of pins. Now, this will always be possible by means of a suitable deformation if, while traveling, the second pins never come to hit the first ones. You have the fixed pins, you have the moving pins. If the second pins never come to hit the first ones, it's okay. The thread may acquire a very complicated form, but this is harmless. So let's try to do this. You see, my psi here is moving toward psi prime. So these moving pins are going inside, so they push, so to speak, the thread, which is deformed this way. And well, this is the picture in the zeta plane or the psi plane. And you can go on like this forever. But it's true that pretty quick you get complicated pictures. And it is by analyzing these pictures that you can prove that the delta omega and delta omega plus satisfy the Leibniz rule, etc. It's really time to stop. Let me just mention that I had prepared another and I prepared a few references about other sources of resurgent series. We have seen pretty elementary examples. Now, something definitely not elementary. This is the origin of resurgence in 1981. ÉCALLE was studying iteration theory or local holomorphic dynamics, a germ at the origin parabolic. But here we map it to infinity, and we are considering such dynamics at infinity. And so the key is to analyze a solution to a certain nonlinear difference equation. And this solution here is called, yes, this is phi tilde, and this phi tilde, this is the equation. Well, this is meant to be the proof. The point is that there is a beautiful equation here, which is called the bridge equation. Delta plus, so the alien operator acting on the solution, is proportional not exactly to phi itself, but to its exponential. So it's a nonlinear problem, but we have the same phenomenon, a bit for the same reason. Here it's more complicated because the equation is nonlinear, but when you apply delta omega, you will get a solution to a linearized equation. And this funny right-hand side is a particular solution to the linearized equation. So this is how it works. And this is an interesting example. It can be viewed in geometric terms as a particular Riemann-Hilbert problem, because after resummation, this formal series, I have no time to explain what it is, but this V tilde Z plus blah, 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 phi tilde of Z, after Borel-Laplace summation, it gives you two sectorial charts in which the dynamics become trivial. And when you compare these two charts, you obtain the so-called horn map, and you obtain something which classifies the dynamics. And that's the beauty. So the moduli space for this problem is encoded by the coefficients which pop up in the bridge equation. So this is the so-called ÉCALLE-Voronin moduli space. And there is a second theorem which is more difficult, which is every such elements, every such pairs can be realized at some moduli. So there is an inverse Riemann-Hilbert problem which is solved. And that is mentioned by Kontsevich and Zolbermann in their last paper as a motivation for their resurgence conjecture, which considers, well, a very complicated problem, but that is one of their motivation, that this particular class of examples. So, well, I have no time, but maybe I can give you these slides if you want to have a souvenir of this mini course.
Yeah, I think the slides would be really helpful. We can put them up on the website if that's okay with you. Great. Let's thank David for a really nice mini course. Any quick questions or comments, especially the virtual participants, since the rest of us will have an opportunity to talk with David over lunch. But if you have any questions, online participants. Any questions from the room? If not, I think we'll have plenty of time for discussions over lunch. So let's thank David again for a very nice mini course.